Hi, everybody. Welcome to the Data Show. My name is Chris Greco. I'll be your host for the next 30 minutes. In this 30 minutes, we're going to talk about data and exactly what that means when it is not normalized. So that's what we're going to talk about today is normalizing data. And basically what you want to do is try to figure out how to compare two disparate data sets, two data sets that may not have the same mean, two data sets that may not have the same standard deviation, that may have to do with two different things. In this case, we're going to compare male heights and female heights. And we're going to compare those as if we were comparing apples to apples. And that's called normalizing data. Now, unfortunately, there has been some confusion about the term normalizing. And this is something that I understand that many statistics teachers and professors are teaching maybe another way of this normalizing, but I'm telling you that normalizing data is not the same as standardizing data. And I think that's an important difference to make. So there's two takes on normalizing. Basically, one is making the data look the same. So if you have something in feet, it's always in feet. You have something in inches, it's always in inches. You have something in, that has to do with certain weight, it's always in pounds. Everything has to be standardized. That's standardization. Okay. The other is transforming the data so that it can be compared to another set of data that may not have the exact same mean, the exact same standard deviation. But there are ways of doing that. There's a way of normalizing the data. Normalizing comes from the term normal, right? Not opposed to abnormal. And I love the way people try to take this and put it into abnormal data. There is no such thing as abnormal data. Normal means that you are going along basically a normal curve, which we described a little bit in the standard deviation one that I did, I think it was last week or the week before. But basically, it's the mean, the median, and the mode are all basically the same. They're in the middle of that curve. They show the most quantity, and that hence that bell curve goes up and then it sits at the top at the peak. That's where the mean, median, and mode all basically line up. Now, does it do that in real data? No, very, very rarely. So what happens is that you're normalizing this data by taking the data that you have and looking at it along that normalizing curve. Now, the problem is I'm going to show you an example of what happens when teachers grade on the curve. And I think this is really, really an interesting phrase to use. And I tell people that are doing this, whenever anybody, professor, teacher, anything says grading on the curve, right? When they use that, run, get in, get another. Grading on the curve is not going to be to your benefit unless you're the smartest person in the room. Unless you know the material inside and out, unless you know you're going to get A's, at least you're going to get at least 90s on all these tests. Because I'm going to tell you right now that what happens is that if the tests are too easy, basically everybody gets 90s, then that's going to be ending up being your C. It's going to be being a C grade. And I'll show you how that works. So everybody gets 90s on tests. Yay, we all get A's. Nope, you all get C's. It's the people that get 95s and 100s that are going to get B's and A's. And that is determined by normalizing, basically talking about normalizing the data. So that's where, you two sets of data and you normalize them so you compare apples to apples. So let's give an example. Two classes take tests, right? The two classes have the same teacher, professor, whatever I'm going to call it. The teacher tells the class that she or he is going to grade on the curve. If the teacher ever says this, you better get the highest score, as I said. Otherwise, if you get an 80%, you could actually end up with a C or lower. The curve references the normal curve, which can be adjusted to show that one class could get an 80% and get a B, and the other class get an 80% and get a C. Grading on the curve assumes that the majority of the class will get a C. That mode that I was talking about, the quantity, is going to peak at the point where that C exists. That's where you just don't want to mess with that. And let's go straight to the examples and just talk about that for just a second here. So so this is we're going to talk about standard deviations and all that stuff in a second. But we're going to talk about class 1 and class 2. So what I did was I just took um, class 1 and class 2, and I'm going to put this up here so you know, so you can see it. So basically what happens is class 1, class 2, these are the grades from lowest to highest. Um, on this one, not lowest highest on this one. So I'll have to, but mock snakes. So basically, this is class 1, this is class 2. So what I did was, in addition to that, I basically standardized the scores based on the mean and the median, right? Or the mean and the standard deviation. Here's standard deviation, and here's what the mean is. So now here's where the problem exists. And let's take a for instance here. Let's say I'm gonna do average, right? And I take the average score, right? So the average score here is going to be 64. If I do the average here, if I do the average here, it's going to be 66. So you have a higher average. But and this is where the situation exists. Yes, you have a higher average here. But what happens is you have to take each of these and normalize these. So here, what we're going to do is we're just going to go to class number 1, and what I did was I put it into a pivot table, and then what I did was I said, okay, where do most of the scores lie? They lie here at the 80. So guess what? Guess what the average score is going to be in this class now? The average score, the C, is going to be at the 80 point. Why? Because this is the peaks. This is how many. Now I know it's only 4 versus 3, but basically, this is what the most scores exist. So this is now going to be our score, our average score. So instead of 64, which it should be, what I'm going to change it to is I'm going to change it to 80. There's my 80. All of a sudden, see what this does? It changed this. This is basically um, what they call changing it into a z-score. So, and the same thing here. So I did class 1 and I did class 2. And see where this is normalized? Where's this normalized? Well, where's the most scores? The most scores are at 70. So 70 is going to be where you're going to have your average. So now you change this to 70. So when I do that, all of a sudden this happens. Now, what does this show me? Well, basically, it shows you that 70 is going to be 0 here, which is, these are called z-scores. Z-scores, and they're done by basically taking a2, which is the, let's say I want to say, okay, if I have a 60 in class number 1, where am I on the curve? Well, I'm here on this curve. I'm at negative 1.21816. Whereas if I get a 60 in this class, I'm at 0.72. Well, I'm closer to the mean, I'm closer to the average, the mode basically is what we're talking about here, than this one is, which means this person right here, even though they got a 60, they're going to get a lower grade score than this person's going to get. Same thing here. Look at this one. This one is -2 if they have a 40. Well, that's a 50. So 40, here's 2.43. This is closer again to 0. This person's going to get a higher grade, letter grade, than this person's going to get. So, or slightly higher, could be a plus, like a D plus, whatever it is. So basically what happens is that is what they call grading on the curve. And a lot of people don't realize what happens with this is that, and this is where teachers and professors, they kind of get away with this, because basically what they say is we'll look at grade inflation. I don't like grade inflation. So basically what I'm going to do is I'm going to grade on the curve, which to me is fair. But basically what happens is it rewards those people that are above that curve. It all depends on your class, right? You can't take an IQ test before you take a class. So basically what happens is you're in the class and all of a sudden everybody is smarter than you. You're trying your best, you get a 70, guess what? If everybody gets 80s and 90s and you get a 70, guess what you're going to get? You possibly could get an F. You may get a D, and you're not going to get anything higher than a C. So basically, and chances are you're not going to get a C with a 70. So basically, you're going to get a D or an F. So now all of a sudden, you're sitting back going, "Do I study harder? What do I do?" Well, basically, no matter what you do, as long as these people are smarter meaning they know how to take a test, they know the material, whatever happens is, it's going to be a hard thing to try to break that curve, to try to get up and do those things need to be done. So it's a tough road to hoe, but that is called grading on the curve. And that's what normalization does. That's what normalizing does. You can compare two different pieces of data by setting the mode as the mean. So this is your mode right here at 70. What you're setting it that as is a normalized mean. So now all of a sudden everything is like, so now I'm sure people that are taking this course are going to be sitting back going, or taking course, or are listening to this, are going to be sitting back going, gosh darn, I never really understood how I was getting. I mean, I was getting 80s and 85s on tests and I was getting C's. Why is that? Well, because the professor decided that, hey, I'm going to do it this way, which it's standard. It's it's fair to everybody, right? And if you happen to get a 70, then guess what? You're going to get a D, possibly an F. And that's how normalization happens. Now, how do we do that with a situation with this is this is basically standard deviation with disparate data. What I also did was I also made it so that I made the z-score here. So this is called a z-score, and z is a statistical term, and basically what it means is normalized score. And that's why, when I take these and I say, okay, here's a 93, I got a 93 here, and I'm at 79. I get a 93 here, I'm at 1.65. Remember, class one was the one that had all the higher, it had all the higher scores. But so what happens is that they're closer to zero. They're actually, if they get a 93, they may not get a B. They could possibly get a C. Here, they're definitely going to get a B, and possibly a B plus or even an A. So this is where it is. And a lot of people sit back and they go, I don't understand, what a normal, what this is and what that is. And what I always tell them to do is look, no matter what happens here, you always have the ability to take a look at to take a look at a normal curve. So what we're going to do is we're just going to look for a normal curve here. But basically, this is the normal curve right here, and this is what we're talking about when we talk about a normal curve. Is this right here? So this is where it's from. And basically, what happens is, remember, I had that score 1.65. So this is up here like this. Okay. Whereas that 0.79 is right here, but they both have 93s. Well, you could sit there and say, guess what? This is now going to be your C right here at the 0. If you're here, right here at the C, that person, the best they're going to get, they're not, they're going to get a C. This is your area of C. This is your area of B. This is your area of A. So unless you get above here, right here, you get a B. Here you get an A. Here you get a C. Here you get a D. So if you're in -1, guess what? You got a D. If you're anywhere between 0 and -1, you have a D. So basically, what do we have here? All right, let's see what we got. We got 93. So right here, we got -1. 78. Guess what? You're in a D. You're in the D range. You're in the D range right here. Where are the D range here? The D range here is around. See, 70 is so here. 69, you're in the D range. So 78, you're in the D range. This. So here. 79, you're in the D range. Here, you're in the D range. So 79 versus 69. And this is done all through developer. And I've shown this in another area, another YouTube video. So this is what we're talking about. When you start comparing apples to apples, all of a sudden it's like, holy mackerel, if I normalize this, I'm not, am I being fair? Absolutely, because they're both based on a normal curve. They're both based normal curve, folks. You can't sit there and say, "Well, I'm going to determine who gets, who's the smartest person, who's not so smart." It doesn't work that way. And also, people are not dumb. No one is dumb. No one is non-intelligent. No one is unintelligent. Basically, what happens is that people have their niche. I mean, I stunk at trying to figure out combustion engines. Well, the guy next to me who couldn't get a C for the life of himself, had a great job of after high school he would go and he would fix engines. Well, he knew combustion engines like crazy. He could figure it all out. So I mean, I was I got probably a D on that test. He got an A because he knew what was going on. So I mean, there's your situation right there. People are smart in certain areas, not smart in other areas. So here is something that is interesting because this is actually height of males and females according to the census data, census.gov. As a matter of fact, I should have do I have, yeah, here it is right here. So th- this is it right here. What I'm going to do is I'm going to put this thing on a banner and then put that out there. So that's where this is found right here. So this is, I mean, this is pretty amazing when it comes right down to it, right? So now you sit back and you go, well, if I compare males against females, males are going to win every time. Males are going to win almost every single time. Look, I mean, look at this. You have 0 all the way to 62. Then all of a sudden you have 63. Well, here 63 is almost the most that you have. So how do I compare the apples to apples? Well, what I did again was I took the female heights and I normalized them. Basically, I said, okay, what's my most female height? 64. That's my most female height, percentage wise. So that's what I have. Okay, good. That's going to be my mean. That's going to be my mean. What about male heights? What are they? Well, they're at 71. That's going to be my mean. So basically, I've set my mean to other areas, right? And that's what I did. So now when I did that, when I do that, all of a sudden it's different. So I had 71 here because 71 is going to be the highest amount, 15.2. Here it's 64. So I'm going to change this to 64 here as my mean. My standard deviation I'm going to leave the same. And basically now I'm going to compare my male and female. So what do I have? So my z-score here is 1.48 at 73. Here it is at 73 inches here with a mean of 71. See, this is all of a sudden, now I'm in the B range if you were talking about grades, because the females are now being compared in a standard score against males. I am comparing apples to apples by making the mean the same as the mode. Now all of a sudden I sit back and I go, wait a minute now. So in relatively speaking, if you're 73 height and the mean is 71, you're going to have a lower z-score, which means you're going to have less people of less a height than 73 than you are at the female, where you're going to have more people lower than 73 because you have a mean of 64. So these are the things when we talk about disparate aspects and we talk about disparate data and we talk about all these different things. That's what we're talking about. And I think that's important to understand and to make sure that you understand what normalizing data is, because otherwise all you're doing is you're just comparing male heights to female heights. Well, males are going to win. They're going to win. And because there's more males at a certain height than there are females at a certain height. Now, is that catching up? Probably. Maybe within the next 10 generations, all of a sudden they'll kind of even up. But right now, females are typically average at a lower height than males. Trying to compare those two, it just doesn't work. But if you normalize them, all of a sudden you can compare them and see that at this height, there are there are more individuals less than this height from females than there are at this height for males. So it just works, right? So I mean, because if you're comparing simple averages, males win out on height, boom. But if you're comparing it by the curve, the females could win based on the mode of that curve. How many are actually at that height? So and that's what we're talking about when we talk about those areas. So, we used Excel to accelerate to illustrate all these areas, and I think that's pretty important to understand. Also, the sampling, you're sampling males and you're sampling females, two different sexes. So basically, there's going to be differences in that data. That's just the way it goes. So basically, what happens is that you're trying to even up those areas as much as possible to be able to make that to be able to compare those two pieces of data in an apples to apples type of situation. Okay, does this produce bias? It doesn't produce bias, and I'll tell you why. Is because it changes the mean to the mode, which some people say could be subjective, but basically what you're doing is you're changing that center of that normal curve, the center of the normal curve, to match the mode, which it does. The center of the normal curve is the mean, median, and mode all put together. What I'm doing is I'm saying, okay, the mode is the center of that curve. I'm making a normal curve from that. So it's not meant to bias, right? It shows a comparison in a fairer fashion than it would under normal situations. Now, is it fair to do that grade on a curve? Absolutely. It's very fair to do that, because basically you're taking the classes and then you're taking the mode and you're figuring out from that mode what your average is going to be, and then everyone else is based on that average. So I mean, this is good to figure out if tests are too easy or too hard, and then be able to adjust accordingly. So I mean, it's a form of weighting, right? We talked about weighting at one point in time. That's usually not mentioned in statistics. It's usually not done in statistics because basically you're changing the data. But are you really changing the data? Well, in some cases, yes, you're changing it from mode to mean. Uh, but basically, what you're doing is you're forming a normal curve from that data. That's what you're trying to do. And to me, it tries to make it in a more fair fashion. So normalization is something that takes two different pieces of data, compares them in a like fashion, making the mean the mode. The normalization uses the mode, and that goes over the mean, so that then we can go ahead and just work it from there. The standard deviation is derived from the mode value and used to compare to another mean, to the other mean, or actually the other mode value. It helps to compare data in order to show a comparison in a relatively objective fashion. So we're trying to use the normal curve as our translation to be able to translate the data into something that is a fair, a fair comparison. So, and we talk about bias, so I think that's pretty important. And I want to make sure that we talk about bias from that standpoint, because I think it's, if you don't do that, basically what happens is that you don't understand how data is done. So basically, it goes something like this. And let's talk about bias here from what we have. So bias. What is data bias? So, bias is something that when we talk about bias and data bias, we talk about following things. So, for instance, let's say that I go out and I interview, oh, I don't know, I interview five people. And those five people, the question I ask them is, what do you think of person X? And three of the people say, I think person X is horrible. I think they were a loner, they liked, violence, those types of things. The other two people said, I think they were great. There's no problem with them. They were really good friends. They were very nice. They were very kind, whatever else. I take the three interviews that said that basically the person was a loner and that was loved violence, and I say, look at this. The individual loved violence and they were a loner. What does that do for me? Well, first of all, it puts that individual in a very, very precarious position because all of a sudden, out of five people, three said this, two said that, but the two I'm not going to include. Media does this all the time. Biased interviewing, they do this stuff all the time. They will go out and actually look for people that say what they want them to say and then publish that in order to make the news more newsworthy. And I think what happens is that, and people say, oh no, that doesn't happen. It happens. It happens on both sides of political spectrum, but it does in fact happen. So you get and the same thing with data. What happens in data bias is that people gather data that proves their point, and then they display that data as if that's the only data to be able to show something that they want to show. So you have to be really, really careful of that data bias. And this is, I mean, this is the same as everything. In my book, A Data Analyst Walks into a Bar Graph, which is available on Amazon. This is a shameless plug, but basically, a data analyst walks into a bar graph. I bring up examples about how this sampling, about how, trying to predict something based on current situations does not in any way, shape, or form include those things that could change in the future. And this is something that we always talk about, and we talk about regression to the mean. We talk about regression to the mean as if it's some weird, oh, regression. Oh, yeah, I know what that is. That's a straight line type aspect. But basically, what happens is regression to the mean indicates that that line sooner or later will go back to center. Again, I've said this before, I've brought this up before, is that uh, let's say that two people marry each other and they're both 6 foot. They have a kid. The kid is 6'3". He or she may meet somebody else and they have a kid, and that kid is 6'6". The other person, they're both of them are 6'3". So this goes on and on. With people sit there and go, "Oh my gosh, it's going to end up people are going to be 9 and 10 feet tall." No, because regression to the mean means that will go back to the average. Now, what are the average heights? I just went through them. So these are the average heights for both men and women according to the census. So basically, what happens is that the more that we talk about this, from, oh my gosh, we're going to have 9 and 10 foot people. No, that's ridiculous, and everybody knows it's ridiculous. That's a funny thing. Everybody sits back and goes, my gosh, if we continue along this realm, and this is you don't continue along the realm. It changes. Things change, and that's called Bayesian probability. That's just things change and they regress to the mean. That's what it is, and that's what it talks about. So, if nothing else, this normalization that we talked about today tries to understand data bias and tries to correct for that data bias in a way that is using the normal curve to be able to translate the data so that you compare disparate data to one another and determine whether or not they are in fact the same or they're different. And that's where it all comes about. So that's it. I mean, that's all I wanted to cover today is normalization. I think I failed in my talking about standard deviation the last time, so I'm hoping this normalization aspect will bring people more aligned with what this is about. Just remember, there's two types of normalization, right? Normalization has to do with standardization, right? Making sure all the data forms are the same and the data columns, and they're all the same units and all those types of things. But normalization means to basically normalize the data to try to make it into that z-score. And the z-score is increasingly important because the z-score basically talks about a standard normal curve. A standard normal curve. Remember, you have a normal curve and then you have a standard normal curve. And that standard normal curve is literally that. It's standard and it's a normal curve. And that's what is that z-score. And that's the center is 0 and it goes either side to 3 or -3. That's a standard normal curve. So that finishes up this edition of the Data Show. Thank you very much for watching. If you have any questions, if you have any type of comments, anything else, please, please, please let me know. You can contact me at candr@statisticssleuth.com. Trademark Statistics Sleuth, so you won't find it anywhere else, hopefully. And that you can contact me through that area. If and I was gonna say if there's no questions, but yeah, I wouldn't be able to tell that anyways. I'm sorry, I'm used to teaching classes. Have a great day and a great week, and make sure, please, please, please make sure to always, always, always check the data. Have a great day.